Hello, everybody, and welcome to today's session of aromatic carboxylic acids. I am Dr. Urmila Joshi, and I will be discussing today aromatic carboxylic acids. If you like the lecture, please subscribe and like. If you have any difficulties, please, my mail ID is shared. So please go through the mail ID and you can feel free to mail me about any difficulty. So let us start with aromatic carboxylic acids. I hope my screen is visible to everybody. Let us wait till this becomes full screen. Okay. Now, your syllabus last semester, you have studied the aliphatic carboxylic acids and their acidity. This semester, the syllabus includes aromatic carboxylic acids. So the first point to be considered is the acidity of aromatic carboxylic acids. As you all know, carboxylic acids are acidic in nature. What do you understand by the acidity? Acidity of any acid means ease of loss of a proton and formation of an anion. This is the anion formed from the acid. Now, more stable the anion, more acidic is the acid. Why is it so? That is because if the anion is stable, the proton will be easily lost. So remembering this that we had discussed in semester 1, let us go ahead to understand the acidity of aromatic carboxylic acids. This is benzoic acid and I have written the benzoate anion. Okay. This benzoate anion can exist in two resonating forms as are shown over here. In one of the structures, what happens is this oxygen gets the negative charge. In the other structure, the lone pair of electrons from this oxygen is shared between carbon and oxygen. As a result, carbon cannot become pentavalent and so this bond breaks. As a result, instead of the oxygen on the left-hand side, the oxygen on the right-hand side gets negative charge. The actual structure is a resonance hybrid of these two equal structures. Please note that these two structures are exactly equal. Okay, and this resonance hybrid is represented by negative charge being spread on this entire group. Is that? I hope you understand this. The negative charge is on one oxygen in this resonating structure. The negative charge is on the other oxygen in this resonating structure. But actual structure has negative charge spread over this entire carboxylate group. Okay. Now, let us see effect of substituent on acidity. But before that, let us try to understand what is the difference between aliphatic and aromatic carboxylic acids. The carboxylate group in aliphatic carboxylic acids is attached to an sp3 hybrid carbon. Just note that the carboxylate is attached to this carbon and this carbon is sp3 hybrid carbon. Whereas the carboxylate is attached to the aromatic carbon over here and this aromatic carbon is sp2 hybrid carbon. Okay. Now any alkyl group with sp3 hybrid carbon donates electrons. When it donates electrons, what it does is it increases the negative charge on the carboxylate anion. And because it increases the negative charge on the carboxylate anion, it destabilizes the anion. Okay. Alkyl group, electron donating, donates electrons. Because of electron donation, the negative charge intensifies. The negative charge on the carboxylate anion intensifies. And because of that, the structure becomes less stable. As against that, just see what happens in case of aromatic carboxylic acids. The carboxylate group is attached to sp2 hybrid carbon. Any sp2 hybrid carbon is more electron withdrawing, and therefore this carbon withdraws electrons and to some extent stabilizes the carboxylate anion. So, benzoic acid as a result is more acidic than any aliphatic corresponding aliphatic carboxylic acid. Okay. Now, coming to effect of substituent on the acidity. First, I have taken an electron withdrawing substituent. This is nitro present at para position. And nitro present at para position is an electron withdrawing substituent. So let us see what happens to the stability of the anion. Okay. This is nitro. It can withdraw electrons from this double bond. As it withdraws electrons from this double bond, nitrogen cannot become pentavalent. So this bond breaks. As a result, what happens is, as a result, what happens is the aromatic ring gets a positive charge. Nitrogen also gets a positive charge, which was already there. And this is the carboxylate ion. Now, it is possible that this structure can also resonate. This double bond can shift over here towards the positive charge. As a result, now this carbon gets a positive charge. Now, have a nice look at this structure. This carbon has got a positive charge, and adjacent to it is a carboxylate anion with negative charge. I hope everybody is following this. When this carbon gets a positive charge and the adjacent carbon has a partial negative charge, this structure becomes a specially stable structure. Okay. This can resonate further, of course. How it resonates further? There is a positive charge on this carbon. This double bond can shift. As a result, the positive charge comes on this carbon. Let me tell you that all these resonating structures we had written for the phenols. Okay, so those who have difficulty, I had discussed this in greater detail in phenols. Okay, just a recap, any electron withdrawing group at ortho or para position will result in the positive charge being on the carbon adjacent to carboxylate. Now this results in a specially stable structure. And so what happens? Because the anion is stabilized, the acid becomes more acidic. As a result, para-nitro or ortho-nitro carboxylic acid is more acidic than benzoic acid. Okay. What happens in case of meta-nitrobenzoic acid? It is exactly equivalent to what happens in meta-nitrophenol. I think all of you will recollect that meta-nitrophenol is less acidic than para or orthonitrophenol. Similarly, metanitrobenzoic acid is less acidic. Now, next, what happens when an electron donating group is present at the para position? We have already learnt in phenols that electron withdrawing group in para position and in ortho position produce equivalent structures. Okay, so just try to understand that this is an electron with donating group. It has two pairs of electrons, so it is electron donating. Now let us see how this forms resonating structure. There is a lone pair of electrons which is shared between oxygen and the ring. Oxygen will not do away with electrons, it will just share. As a result, this carbon becomes pentavalent, it cannot. So the double bond breaks and the negative charge comes here, right? Now, this negative charge can move further in the ring. Just see how this comes over here. It is shared between these two carbons. As a result, this carbon becomes pentavalent. It cannot. So the negative charge goes on this carbon. That is what I have written in the third structure. Now look at this structure. There is a carboxylate anion and adjacent to it is a negative charge. So two negative charges close by to each other make this structure more unstable. Okay. And because this structure is more unstable, any electron donating group at ortho or para position result in a carboxylate anion that is less stable. And because it is less stable, any electron withdrawing group present on the para position or ortho position, para or ortho of benzoic acid make the resultant compound less acidic. Is that clear to everybody? Now remember, you should be able to write these resonating structures. I forgot to mention this, the negative charge can move further. This can be shared between these two carbons. As a result, this carbon becomes pentavalent, it cannot, and so the electron pair is returned to this carbon. Okay? So, in a nutshell, if there is any electron withdrawing group that increases the acidity. Now, which are electron withdrawing groups? Electron withdrawing groups, I will write here, electron withdrawing groups. Okay. Electron withdrawing group, nitro is an electron withdrawing group. Carbonyl, to which anything is attached, I will put here Y. It can be acid, it can be ketone, it can be aldehyde, it can be ester. All these are electron withdrawing groups. Why? Because here there is a partial positive charge. So it can only withdraw electrons. Okay. Whereas there are some electron donating groups which donate electrons by resonance. Which are they? OH is there. Any group in which the atom directly attached to benzene ring has pairs of electrons. These are electron donating groups. Even halogens are electron donating by resonance. Okay. OCH3 is there, so on and so forth. So just remember, when there is an electron donating group attached at ortho or para position, the acidity is reduced. Whereas if there is an electron withdrawing group attached at ortho or para position, the acidity increases. Now coming to some simple methods of synthesis of carboxylic acid, aromatic carboxylic acids. First is oxidation of alkyl benzenes. Okay, when you oxidize toluene, you get benzoic acid. When you oxidize benzyl alcohol, then also you get benzoic acid. Please remember that upon oxidation of ethyl benzene also you get benzoic acid, because it is not possible to stop the oxidation at this carbon. The complete aliphatic chain gets oxidized and you get benzoic acid. So oxidation of alkyl benzene is one of the important methods for synthesis of aromatic carboxylic acid. The second one is carbonation of Grignard reagent. Everybody is aware of the Grignard reagent. Okay, any alkyl or aryl halide, when treated with magnesium and ether, results in formation of a Grignard reagent. In this case, it is ArMgBr. Okay, you treat this with carbon dioxide and you get a magnesium salt of aromatic carboxylic acid, which upon hydrolysis, acidic hydrolysis, gives you aromatic carboxylic acid. So it is easy to remember, this is Ar, this is ArCOOH. So one carbon has been added. Where does it come from? It comes from the CO2. Okay. The third method of synthesis of aromatic carboxylic acids is hydrolysis of nitriles. Okay, nitriles are same as cyanides. Okay. Now, any aromatic nitrile, when it is hydrolyzed, gives aromatic carboxylic acid. Now, how to get this aromatic nitrile? Aromatic nitriles are obtained from aromatic amines. Aromatic amines can be converted to their diazonium salts. And these diazonium salts, when treated with copper cyanide, result in formation of ARCN and then subsequently give ArCOOH. So this is a method for converting an aromatic amine to aromatic carboxylic acid. So we saw three methods for synthesis of aromatic carboxylic acids: carbonation of Grignard reagent, hydrolysis of nitriles, and oxidation of alkyl benzenes. Please do not write hydrolysis of ester as a method of synthesis of aromatic carboxylic acids. That is because esters themselves are obtained from carboxylic acids. Okay, now reactions, very few reactions. First is conversion into functional derivatives, that is acid chlorides, esters, amides, etc. Now, when acid is treated with thionyl chloride or PCl3 or PCl5, it results in formation of acid chloride, ArCOCl. And this is a simple reaction. Second, when acid is treated with an alcohol in presence of protons, it results in formation of an ester. Let us revise the mechanism that we had studied in semester 1. This is an acid. When the acid is protonated, this results in a structure where the proton is taken up by the carbonyl oxygen. Now, because the proton is taken up by the carbonyl oxygen, now the attack on this carbonyl carbon becomes simpler. The nucleophilic attack on the carbonyl carbon becomes simple. As this oxygen lone pair is approaching this carbonyl carbon, carbon cannot become pentavalent and therefore this bond breaks. So the resultant structure is this. Now, in this structure, there is a positive charge on this oxygen because there is a proton attached to it. there is a proton shift which takes place, and this proton shift upon this proton shift, what happens is this regains its electron pairs and one of the OH group becomes OH2. What is the advantage of one of the OH group becoming OH2 is this becomes a good leaving group. Okay, this leaves with a pair of electrons and the resultant compound is an ester. Okay, the mechanism is same as what we had studied in semester 2. Now, there is another way of synthesizing esters. Instead of taking acid and alcohol and in presence of protons in a single step reaction, you can convert an acid to an acid chloride. Okay, when you convert acid to acid chloride, the reactivity for ester formation increases, and then this acid chloride easily undergoes reaction with alcohol to form an ester. Okay, now this reaction is faster, this reaction is slower, but we can do things. This is a one-step reaction plus environmentally problematic halides can be avoided in the one-step reaction. So what we can do? We can, this is the reaction, acid reacting with alcohol forming ester and water. If we remove water continuously, the equilibrium of this reaction will shift towards right and the reaction will be speeded up. The last point here is the nature of alcohol that you are using also affects esterification. Methanol reacts fastest, followed by any primary alcohol, then followed by secondary, and tertiary alcohol reacts slowest. Now, why does this happen? Look at this step where the alcohol is attacking the carbonyl carbon. Okay, the carbonyl carbon from an sp2 hybridized status is getting converted to sp3 hybridized status. So the size of R will matter over here. More bulky the R, there will be more crowding in the transition state and the reaction will slow down. That is why primary alcohols react faster than secondary and tertiary alcohols nearly do not react in this esterification reaction. Okay. These are reactions of aromatic carboxylic acid, other reactions. Acid can be converted to acid chloride or ester and then treated with ammonia to get amide. Why acid cannot directly get treated with ammonia is because OH is a poor leaving group and OH does not leave unless it is protonated. But protonation of this will cause a problem with this. The lone pair of electrons will not be available for attack on carbonyl carbon. So you either convert it to acid chloride or ester and then treat it with ammonia to get. Then reduction. Acid can be treated either with lithium aluminium hydride or with B2H6, okay, to give the corresponding alcohol. And this reaction, how it is useful, just try to understand. You know that long chain fatty acids are obtained from fats, but these long chain fatty acids naturally available contain only even number of carbons. Okay. You can change that by this reaction. You convert the acid to an alcohol. Alcohol can be easily converted to alkyl halide. The alkyl halide can be treated with KCN to obtain ArCH2CN, and this ArCH2CN can be hydrolyzed to give ArCH2COOH. Okay, so one carbon you are adding to the fatty acid and making the unnatural fatty acids. Last, electrophilic aromatic substitution. The reaction COOH, as you know, there is a carbonyl carbon which is partially positively charged, and so this is meta-directive. So any reaction of electrophilic aromatic substitution will give a meta-substituted product. I have shown here two reactions. So that is all about carboxylic acid. Here are some questions. You may note down the questions. And please feel free to write to me if you have any doubts. My mail ID is given in the first slide. So, thank you so much. And